Welcome back to The Explainer. Today, we're tackling something that is literally groundbreaking, one of the most terrifying yet totally fascinating geological phenomena on our planet. I want you to imagine the ground beneath your feet right now. It feels solid, right? Dependable. It holds up massive concrete buildings and sprawling highways. Now imagine that exact same solid ground suddenly losing all its structural strength and turning into a soupy, quicksand-like liquid in a matter of seconds. Sounds like a sci-fi movie, but it's the very real threat of earthquake-induced liquefaction. In this explainer, we're going to break down exactly how solid Earth transforms, why it happens, and how human engineering is fighting back. So, to really wrap our heads around this, let's start with a bit of a weird question. What on earth does a violently shaken bottle of champagne have in common with a sinking building? Think about what happens when you shake up that champagne before popping the cork. You're building up this intense, trapped gas pressure, right? Well, incredibly similar buildup of pressure happens beneath the Earth's surface during an earthquake. Except instead of volatile gases, we're talking about immense geological pore water pressure that's trapped right between the grains of soil. And when the ground starts shaking, well, all that pressure has to go somewhere. All right, here is our roadmap for today. First, we'll look at when solid ground liquefies. Second, the types of ground failure. Third, the impacts on the built world. Fourth, identifying high-risk areas. And finally, engineering and mitigation solutions. Okay, let's jump right into part one, when solid ground liquefies. If we zoom way in, down to the microscopic level, soil particles basically just rest right on top of each other. They bear the weight of everything above them through constant physical contact. But during an earthquake, the intense shaking causes these loose grains to suddenly rearrange themselves. This drastically and instantly spikes the pressure of the water trapped in the tiny spaces between the grains. The water pushes back with such incredible force that the sediment particles literally lose contact with each other. They get forced apart. And just like that, the soil completely loses its stiffness and starts behaving exactly like a liquid. So this entire breakdown happens in a few clear sequential steps. You need loose, fine sand, and it has to be saturated with water. Once an earthquake strikes, and historically it only takes a magnitude 5.0 to kick this off, which isn't even a massive quake, the shaking forces the water pressure to spike. The particles float apart, and boom, your previously rock-solid foundation is now basically quicksand. Eventually, that trapped water squeezes its way out, often violently erupting at the surface, which actually leaves the soil in a much more compact state afterward. Moving right along to part two, types of ground failure. When the ground turns to soup, it generally fails in one of four very specific ways. First up, and definitely the most dangerous, are flow failures. These happen on slopes steeper than 3 degrees, and we're talking about entire blocks of land sliding at speeds up to 10 kilometers per hour. It's terrifying. Then we have lateral spreads, which happen on much gentler slopes, where blocks of earth essentially just crack and slide horizontally. If the ground is totally flat, you get ground oscillation. The earth literally ripples like an ocean wave, spinning up water and sand. And lastly, there's loss of bearing strength, which is exactly what it sounds like. The soil simply gives way and drops whatever happens to be built on top of it. When you visualize these mechanics in a cross-section, it's wild. You can see a violent flow failure, essentially avalanching down a steep incline. Contrast that with lateral spreading, where the surface literally cracks into sliding puzzle pieces. On perfectly flat ground, oscillation creates these crazy conical sand blows. People sometimes call them sand volcanoes that just erupt right onto the surface. And with a loss of bearing strength, a heavy building just hopelessly tilts and sinks as the liquefied zone underneath completely fails to support its weight. Let's transition into part three, impacts on the built world. The sheer scale of this hazard is honestly staggering when you see the real-world aftermath. In the massive 1990 Luzon earthquake in Dagupan City, multi-story commercial buildings literally sank straight down into the earth. They just lost all bearing strength. Compare that to the 2013 Bohol earthquake, where massive, gaping surface ruptures stretched completely across roads and fields. That is a textbook example of lateral spreading just tearing the built environment to shreds. But wait, because the chaos isn't just happening on the surface. There's a whole hidden nightmare underground. When that pore water pressure spikes, it doesn't just make heavy things sink, it actually makes buoyant things float. Empty underground storage tanks and sewer manholes are violently pushed upward, literally bursting right through the pavement. Meanwhile, power poles get pulled completely over, and stiff underground utility pipes just violently snap apart as the ground spreads laterally toward nearby river channels. It's just total, catastrophic infrastructural failure. Which brings us to part 4, identifying high-risk areas. So why does this happen in some places and not others? It all comes down to a striking difference in soil composition and age. Liquefaction almost exclusively targets loose, well-sorted, water-saturated sands. As a rule of thumb, the younger the sediment, the higher the risk. We're talking about Holocene sediments, meaning stuff laid down less than 10,000 years ago, usually found in river deltas and floodplains where the water table is super high. On the flip side, if you're sitting on old, deeply compacted earth or soil with a heavy clay content, like over 15%, you've got natural resistance. Those clay particles bind together in a way that actively fights off those water pressure spikes. And when we map out those specific geological rules, we get regional susceptibility maps that are incredibly revealing. Take the Philippines, for example. When you look at their national hazard data, the danger zones almost perfectly hug the coastlines and major river valleys. By taking historic earthquake data and combining it with a deep understanding of where those young, soggy, sandy deposits actually are, geologists can tell us with scary accuracy exactly where the ground is most likely to turn to liquid. Finally, let's hit part 5, engineering and mitigation solutions. Okay, so how do we deal with this? Well, the absolute best defense is simply avoidance, using those hazard maps to zone vulnerable areas appropriately so we just don't build critical infrastructure there. But obviously, real estate is precious, and sometimes avoidance just isn't an option. That's when the engineers step up. We can mandate ductile, flexible utility connections, so pipes bend instead of snapping when the ground shifts. But even better, we can actually change the ground itself. We can forcibly compact the soil to artificially densify it before we even lay a brick, or we literally excavate the weak sand and swap it out for firm, dense, clay-heavy material. From a structural engineering standpoint, instead of using standard, separate footings for a building, we can pour a massive, rigid mat foundation. Think of it almost like a heavy concrete raft. If a localized patch of soil liquefies underneath, this thick mat is strong enough to bridge the gap and transfer the heavy load of the structure to the adjacent stable ground. Alternatively, builders can just bypass the danger zone entirely by driving massive concrete pillars, called piles, deep down through the liquefiable sand until they anchor firmly into the solid bedrock below. And you know what? We have rock-solid, pun intended, real-world proof that these techniques actually work. During major historic quakes in highly prone areas like California and New Zealand, facilities that invested the money in prior site improvement, where they compacted or replaced the soil before construction, experienced practically zero damage. They stood completely strong, even as the untreated ground right next door suffered violent lateral spreading and catastrophic settlement. The engineering absolutely works. We're going to end on this thought today. While we absolutely cannot stop earthquakes from happening, our deep understanding of sediment mechanics and geology allows us to build a resilient world directly on top of shifting sands. The next time you walk past a massive construction site near a river or coastline, take a second to appreciate the invisible, dense foundation work happening below the surface. Because even if the Earth temporarily turns to liquid beneath us, our structural ingenuity ensures we aren't going down with it. But it does leave you wondering, doesn't it? How deep is the bedrock beneath your own home, and what exactly is resting between you and solid ground?